Okay, it works, perfect. Yeah, welcome to this session about garbage collection. Trash Talk is the name. And, more people coming. Yeah, don't be shy. Come down here. Come. Okay, so does it work? Yeah, so my name is Gerrit Grunwald. I'm working for Azul, as you can see. But that should be enough about me. We talk about memory management. So first of all, you are all Java developers, or on the JVM at least. Also not. Okay. Why are you here? So yeah, this is about memory management. And in the JVM, this is automatic, right? So why care? Huh? Well, it has an impact on application performance, first of all, and also on the responsiveness of your application. And in the end, also on the system requirements, so that you need to run your application, right? So it's not that unimportant as you might think. So first question to the audience, who is setting a specific garbage collector in his production environment for his application? Okay, that's good. The others just take the default, which is also good. It's not a bad thing. It's just, you just take it as granted that it works, which is nice. To give you a little memory how it works in the JVM, it's just a short overview, right? So we have so-called stack frames, and this will be created for each thread in the application. And they have local access. That means they are thread safe, and we store primitives and references in there. And then we have the heap, where we store the actual objects in the JVM. And then there's another thing, which is the meter space, where we have, in short, everything that's needed for the JVM to handle classes and these kind of things, right? But in this session, we don't talk about the meter space. This is more or less only thread, mainly the heap, because this is where the objects are. So and the heap, it's shared access, so it's not thread safe. And we need garbage collection in the heap, not in the stack frames. They grow and shrink automatically, so we don't have to take care about these ones. And to give you an idea, to make it easier to understand, but first of all, this is all the examples that I show you. This is very basic, simple examples, right? So it's way more complex than I show you, but it gives you an idea. So here, this little program, I hope you can read it. Very simple. You see I have a few records, persons, and then I put them in a list. And if we take a look at the stack frame, then it will look like this for this specific application, right? So we have the persons there, the references to the persons, and the reference to the person list. And on the heap, we have the actual objects. So for each person, we reserve some memory, and also for the list. And then you see the references from the stack frames, they point into the heap, to the actual position of the objects. And you see there's also internal references from the list internally in the heap to the objects, right? So what happens if, so all these are reachable. When I say reachable, I mean we can reach it from the stack frame, we can reach the objects in the heap, right? Following the references, that's the idea. So if I set the P1 here to null, so you would expect, okay, the object is null, so it's gone. Well, it's not really, because if I just would print out the P1, that is null. If I get to persons, get the first object from the persons list, it's still there. The reference from the stack frame is gone, but the internal reference from the list still pointing to the existing object in memory. So that means I still can access the object. And sometimes that's the problem. If people just setting objects to null, assuming they are gone, there might be still some internal references in collections that still point to these objects. They are not gone. So they still take up space on the heap. Right? So I can still reach it and get the result. If I set the list to null, then this internal reference is also gone, and then I only can reach these three objects from the stack frame. All the rest is gone. And in principle, this stuff is garbage, right? It's lying around in the heap, consuming memory from the heap, and we can't access it anymore. So that means we have to get rid of it, of these garbage objects. And how to do that? This is the idea of garbage collection, right? So do we have any people here with C++ background? Okay, One, obviously. And you love the mem alloc stuff and free. Okay, good point. So what is it? In short, it's a form of automatic memory management. There's also something like called reference counting or automatic reference counting. That's a different approach. That is, for example, used in Swift. And there's no better or worse. This is just a different approach. Both have their advantages, pros and cons, right? So it's made to identify and reclaim no longer used memory areas and ensure efficient memory utilization so that you don't have to take care about it. And that's the main thing. So you shouldn't worry about memory management. That's the idea behind garbage collection here. So before we start, who knows what stop the world means? Okay, so if not, it's not a shame. It's all good. I will explain it to you. It's more or less we halt all application threads, and then we clean up the heap, and then we continue. So it looks like this. So we have the application threads running, and then the JVM sends a signal, right? It's a save point signal to all these threads, and they will stop. Once they stop, they reach a so-called JVM save point. That means now all application threads are stopped. Now the JVM can clean up the heap, right? It will do it in more or less one or multiple threads. And once this is finished, it will continue running the application. And in this orange period here, it's stopping the world, means your application doesn't work at that moment. So assume you have a web service, you ping it, and now we're in this orange area, it won't respond, right? It's more or less dead for that moment. And that could be a huge problem because these pauses can be in the seconds, right? Can be really long, like 30 seconds. Depends on how large the heap is and all these kind of things. So that's, and most people don't know it these days because we don't have these problems anymore very often, but in the past that was the problem, right? Like 15, 20 years back, garbage collection, stop the world pauses have been the biggest problem at all. So before we start with the collectors in OpenJDK, we have to understand how collectors work in general. So I just put the three most basic principles here, which is the non-moving collector, mark and sweep. Who heard about mark and sweep? Probably a lot of people. But it's always like, okay, I don't know exactly how it works. Well, I try to make a little animation to make it easier for you, right? So this should be the heap, or the gray squares or rectangles that you see here. If they are gray, they are free, unused. If they are blue, they are referenced. That means they are in use, right? If they are purple, they are dead, garbage. If they are blue and they have this little red square on the upper left corner here, then that means they are marked by the garbage collector as live, right? And then if they have a number in there, this is not for this one, but for later ones, that means if you have a garbage collector that's running, and it collects the garbage, then we have also objects that survive this garbage collection cycle, right? And this number is the number of how often it survived the garbage collection cycle, right? And this is important for other collectors. So let's take a look because it makes things easier. So we start collecting, allocating memory, and you see objects die quite fast. So they get purple after some time. Once we reach the end, we have to stop the world, mark all the live objects, remove the rest, and then continue. So we mark, stop, mark, remove, continue, right? You see already the problem here. Because we remove objects, we don't move them around, so they stay on their place, and the whole heap gets cluttered. In this example, this isn't a big problem because all the objects just consume one memory cell. But in reality, and that's what I mean with this is very simple, very basic, in reality, the objects can consume 10 of these rectangles. And then you need one space of 10 rectangles to allocate. And if it's not available, then you run out of memory. That's the problem, right? So that's good because we don't have to move objects around. It's just we allocate memory. If it dies, we just remove it again, and then we allocate again. So, but you see the problem here, it's fragmentation. And some people might be old enough to remember Windows 3.11. You know, this disk defragmentation looks like this, right? Same problem, exactly the same, right? We have the same problem in the heap if we just do mark and sweep. Well, To get around that, there are also so-called moving collectors, and we have two different ones. We have the compacting collector and we have the copy collector. So let's take a look at the compacting collector. Pretty much the same. We do exactly the same that we did before, but now when we stop, we mark, we remove the rest, and then instead of just continuing, we just compact. That means we just put everything, in this case, on the upper left corner. Right? Let's take a look at that one. So we allocate memory, objects die fast, which is a fact, not only in Java, it's in all languages. So we stop the word and we stop it a little bit earlier now. Right? We stop it now. Mark, remove, compact, continue. You see the advantage, right? Because now we always have free space ahead of us. We can just freely allocate, and that means allocation is fast. And that's what we claim for. We would aim for. We would like to have fast allocation because that makes your application fast. Problem is, we have to move objects. Remember from the first slides that I showed you, we have the stack frame and we have the heap. And from the stack frame, we point to the objects in the heap. Now we move the objects on the heap. Means we have to update these references in the heap, right? That point to the right objects. As soon as we start moving things around, we have to update these references. That means it takes a little bit longer. But in the end, it's easier to allocate, which makes the stuff faster. Okay. Problem here, we need a little bit of headroom, because if you, and again, very basic example, right? We have bigger objects. If we would like to free space on the left side to compact, we have to copy it first somewhere. So we always make sure that we have some spare space, in this case on the right side, to copy stuff there and then copy back, right? To organize everything, to make it look like this, right? This is the problem here. We need some headroom. And that depends on the heap size, right? So it could be 20 to 50% of the heap. You just need to copy stuff around for moving objects. The next one, which is the copy collector, and this is the last of the three basic principles that I will explain to you, you will see it's different. It looks different, because now we have two different areas here. They have the same size. The idea is we have a to space and we have a from space. And we allocate in the to space first, right? As we saw before, if this fills up, we stop the world, we mark all the live objects, and we copy the live objects to the to space. And before we do that, we toggle the spaces. You will see that the orange and gray area, they will always toggle when we stop the world, right? That means the former to space becomes the from space. And then we copy from the from space to the to space. That's the reason for the names. And then because we copy always in an empty space, we don't have any problems with allocation, right? Because it's always free. We can just allocate freely, and it's directly compacted. You will see that. Let's take a look. So we allocate, objects die, right? As we saw it before. Now we stop the world when it's filled up. We mark everything. And then we copy the live stuff directly. And now we see the toggle here. Mark, copy. And then we can directly wipe out the old space completely, because there's no live objects in there anymore. You might see already the advantage here. It's two. First thing, we don't have to move stuff for compacting. It's always compacted. And if we free the old area, we can just wipe it out completely. And freeing, and I didn't explain it here because we don't have the time. I usually do that when I do it at Java user groups. Freeing also takes time, because we have to step through every object and check, is it used or not? And this we have to do with the whole heap. It might take a long time. If you have a huge heap and you have to access every object to check if it's live or not, to free it, then freeing takes time. And in this case, because we only copy the live objects to the other area, we can directly free the whole area without checking. That makes it faster, right? Okay, so, but it also has some drawbacks. The drawbacks here is, if we have objects that live for a long time, we have to copy them every time, right? If they live for the whole lifespan of your application, you copy them with every cycle. You have to update the references every time, which also takes time. This is the drawback with this one, but it has these two advantages. And as you also see, we need twice the amount of memory for the heap. because we need to be able to copy the whole thing in the worst case, okay? So this is the 3 basic principles, and from these principles you can build another one, which is a generational collector. Who heard about generational garbage collection? Who knows how it works? Yeah, exactly. This is exactly the problem. So everybody says, yeah, I heard about it, but how does it work? Not sure. So, okay, let me explain it to you. It's pretty simple. First of all, we have the weak generational hypothesis, and that only means, in simple words, objects die young, and that's a fact. So it looks like this. You probably saw that chart somewhere. So on the y-axis, we have the number of objects, and on the x-axis, we have the lifetime of the objects. You see, a lot of the objects die directly after we use them, or created them. And the reason for that is, for example, this is one word I say is scope. Everything that you create in a method, once you leave the method, everything in the method is garbage, right? And if you used to have lots of small methods, that we should have because it's better maintainable, then we create a lot of garbage all the time. So that means we have lots of objects that die young, and then we have some objects, they live a little bit longer, and then we have just a few objects, they really live for a long time. Okay, if we now use these principles that I show you to shape a heap and the garbage collector for this behavior, then we use something that we call the Eden space, right? Which is the yellow area here, and we create objects in the Eden space. Eden space doesn't have to be very big, because objects die young. That means it can be small enough to hold all the live objects, at least for one cycle, and then we can directly do a garbage collection in here very quickly because it's not very big. For the medium living objects, we use a copy collector. And this is also called survivor spaces, right? So it's the space where objects will be copied that survive the first garbage collection cycle. Then they stay in this copy collector, will be copied back and forth for a specific amount of time, and usually there's a counter that counts how often does this object survive the garbage collection cycle. And if it survived, let's say, 15 times, we just promote it, that's the name for it, we promote it to the to-nerd space. That's the old generation. Every object that survived more than 15 times, in this example, for example, right? Okay. So we now have these 3 different areas here, and we talk about the so-called young generation, which is the yellow and the copy collector here, the Eden and the survivor spaces, and the old generation, which is the blue one. And we have different garbage collection cycles for each of these generations. So that means we have a minor collection that is in the young generation, and we have the major collection that is in the old generation. Different collectors also, right? So that means also the principles of how to clean it. And then there's a so-called full collection. That means both areas will be collected. This is just because some people mess up major collection, full collection. Full means really minor and major means only the old generation. Okay, again, little example makes it more easier to understand. So you will see we allocate stuff in Eden only. Once it's full, stop the world, can be very short because it's a small space. Everything that survived Eden will be copied in the copy collector. In this example, after 3 iterations or 3 times surviving the garbage collection cycle, objects will be promoted in the to-nerd space to the blue area. And then in the blue area, you will see, I will do that once, and once we copy the first things into the blue area, I will do fast forward because that takes some time. And then you will see some kind of a wavefront moving through the blue area, because even there, objects will die. They live longer, but they will die at some point. And then, once the blue area fills up, we do a full collection. But let's take a look. So, we start allocating, objects die, live stuff, stop the world, mark, copy into the copy collector or survivor space, and then again. So we fill up the survivor space. Even there, objects will die. We mark them, copy over, add the stuff from Eden, and so on. Now, still not full yet. Objects die too fast. Now we have the first promotion. So and now you see it's now faster. But you might see the advantage here. We can allocate quite fast. Only stuff that survives long enough will be promoted. Do you see the wavefront moving to the blue area? Now we have to stop the world in the blue area, we mark and compact, and then we copy everything from the young generation also to the old one. So let's see. Mark, compact, everything that's live, copy, continue. This is how it works. Like I said, very basic principle. Way more complex in reality. But this is, you get the idea, right? So what we solved with this collector is objects that live for a long time, we don't have to copy them all the time in the copy collector. Objects that die very quickly, we can directly allocate and get rid of them in the Eden space. And stuff that lives for a long time, and this is a little bit of the drawback of this collector, the blue area usually is quite big. The reason for that is you don't want to do garbage collection that often in a big space. So that means we fill it up, and once it's filled up, then we have to do the garbage collection in the old generation, and because it's a huge area, might take longer. Right? So this is the reason why this principle is good, but it might have long garbage collection pauses as soon as the to-nerd space run out of space. Okay, this was all just for single-threaded stuff. Right? We stopped the world. What about doing concurrent collection? We allocate memory, at the same time we do garbage collection. How does it work? I mean, concurrency is hard, right? So just two things here. It's concurrent marking. That means the collector has to find the live objects and mark them, set the mark bit. And I just will show you some problems you can run into. So if we do that, usually we start from the root, which is the stack frame, that's the square. And the collector just starts and follows the references to the objects. He finds the first one and marks it as reachable, right? And then it said, okay, it's live. Then it goes on to the next one. And then suddenly, because now it's concurrent, the application thread decides, oh, you know what? I remove this reference because I don't need it anymore, and I create a new one. Well, the garbage collector already passed the first cycle, right? So it was live. I know that. I'm done. And it continues. So it has no idea that there is a new reference here, right? So it will continue following all the references, mark everything live. And once it's done, it won't really find this one, and it will remove it. So the application will crash, right? So what can we do? Well, there's one thing. I'm not sure if you heard about it. Who heard about barriers? One? Okay. So to make it very easy, there are read and write barriers, and a barrier is like a hurdle. It's some piece of code that will be executed every time you read a memory cell or you write a memory cell. Right? This is the idea. So you can already imagine that if I have to do that every time I read a memory cell, the code must be very efficient. Right? Because if you have to execute lots of stuff, then the whole thing will be very slow. Okay? So it's a mechanism to execute memory management code when a read or write on some object takes place. Okay. So this is used. We have these different generations, and I told you we have different collectors in the young and in the old generation. If we now have references that point from one generation to the other, and we have different collectors, somehow the collectors need to know, right, if there is a reference from the other generation in this one, or the way around. You can use barriers to do that, but it leads too far, so we don't go into that. You can also use barriers to synchronize between the allocation thread, the mutator, and the collector thread. Right? So this is also used in other collectors. We will look at that a little bit later. Okay. Oh, and one more thing. Because we have around 75% reads and 25% writes in a typical application, read barriers are way more expensive than write barriers. Right? This is just a fact. Because if it's triggered 75% of all memory accesses, then of course it has to be very efficient here. All right. Again, now with the write barrier in place, so garbage collector starts, same thing as before. JVM installs a write barrier before each memory access here. So the garbage collector just goes there, okay, it's reachable, it's live. Next one, it's reachable. Suddenly the application thread steps in and removes the reference. And in this case, right, for this example, that means every reference that was removed, mark the object it was referencing to, mark it as reachable, not live, right? So the write barrier will take care about this, that this object will be marked as reachable. So the garbage collector goes on, right? Finishes his job. Once he's done, there's now a second phase, and it's called the remarking phase. Because you see, everything is reachable that the garbage collector touched, but the write barrier marked there's another object which is reachable. So now there's another stop the world pause, and the garbage collector do a remarking phase, right? He does a remarking phase, and he finds this one, marks it as live, and then it continues. So there's an additional step involved to do that, and you can imagine it takes more time to do it, but with this you can make sure that concurrent marking works. This is just one approach. There are different ones. The next one, concurrent copying, that's even more complex. So think about, we have objects in the heap. We do the compacting step, right? So now that means we move an object from one space to another one on the heap. We have to update the reference that points to the object. At the same time, the application can access the object. So this is very tricky. So if we do stop the world, it looks like this. We have an object in the from space, right? And we have headers, and we have on top you see the squares, that's the stack frames. They point to this object, the references, it's all good. So stopping the world, no application threads running. We copy the object to the new space, easy peasy. Then we install a forwarding header in the old one, and then we update all the references to the new space. Now all the references point to the new area, no problem. We remove the stop and continue working. That's stop the world, easy. So let's do that continuously, concurrently. So we have the same object. Now we copy it to the new space. We don't stop the world. And then we start updating references. So we install the forwarding pointer. Oh yeah, some references are already updated, and both objects in this moment are reachable now. That means if the application now accesses the object, some points will access this object, the other one the other object. This is really nice. You don't want to go there. So how to get rid of this situation, right? So there's a way to do that. There are different ways. One way is a so-called Brooks pointer. In the Brooks pointer, what we do is we install a forwarding header in front of the object on each of these objects, right? And this forwarding pointer points to the object header itself. This doesn't make sense at all at the moment, right? You will see when it makes sense, because now we copy this object to the new location, and we let the forwarding pointer point to the new object header, okay? And now, and this is now, nobody knows about the copy because we didn't start updating the references yet. And now what we do is, we just update the one pointer, and this is an atomic operation. It's just pointed to the new header, and then we start updating references. And what's happening now is everything that points to the old object will forward it to the new one, and everything that was already updated is already pointing to the new one, right? So this is the idea, very basic again, keep that in mind, of a Brooks pointer here. And because of this atomic operation of just moving the one reference pointer, the forwarding one, to the new header, that makes it all work. And yeah, it's used, for example, in the Shenandoah collector. They use the Brooks pointer to do this kind of things. Okay, and then we update, and once we are done, and this is another thing you have to keep in mind, I just tell you, oh, we just copied the object. This is on the heap. We need this amount of memory, and we need to keep it until we updated all the references, and then we can remove the old one, right? Until this point, we have to keep it. Then we remove it from the heap, and then it's finally gone, and everything's working on the new object. That's the idea. You don't have to remember all this, right? It's just that you get an idea how to get rid of this stuff. Now we take a look at the collectors on the JVM, and if I say JVM, I mean OpenJDK. Is someone on OpenJ9 or J9 here? Because they have different collectors. Very similar, but different. We start with the oldest one, which is the so-called serial collector. And to make it short, I just have this overview slides. I won't go through all the stuff. On the left side, you will find the availability, since when, it's in all JDKs, if it's parallel or not, concurrent or not, generational or not, right? So all these things you will find on the left side. Then on the right, there's choose when, like if you have a single core system with a small heap, in this case, let's say 4 GB, then it's a good one. If you don't have any pause time requirements, that's okay, because there's a reason for that. I will explain it to you. And this is best suited for single-threaded application, development environments, things like that. With this collector, there's one specific thing, because if you don't define your garbage collector in your application, the JVM will choose one for you. Usually, that's the default collector, and in the current JDKs, this is the G1, which is fine. But there's a little bit of exception, and the exception is if you have a single processor system, right? Just one CPU, or if your memory or your heap here in this case is less than 1.8 GB, the JVM will select this garbage collector for you if you don't specify anything. And the problem why I mentioned this, the problem is if you run something in Docker containers or in containers. Who's running in containers here? Yep, applications. Who's running in small containers, like 2 GB? Yeah? You might run into this problem. If you decrease the heap size to less than 1.8 GB, you will get this garbage collector. That might lead to garbage collection pauses that you don't expect and you didn't saw before. So be careful if you do that. It doesn't mean this is a bad collector, but it can happen, right? So if you just shrink the heap size to less than 1.8 GB, the JVM will select that one if you don't select a specific garbage collector. This is something you have to keep in mind. Why is it sometimes a problem? You see, we have the young generation and the old generation collector, and it's a single thread that is doing the garbage collection in both. If you have a larger heap, that means if it's in the gigabyte range, then one thread to cleaning it up takes some time, okay? So this is the problem. If the to-nerd space in this case, for the young generation, probably not the big problem because the space is small. But if you have a to-nerd space that's bigger and you have just one thread, cleaning it up might take some time, right? This is the reason why it's the serial one, right? Just one thread. Okay, the opposite, the parallel collector, which is also available in all JDKs. And this is more for multi-core systems, still with a smaller heap. If you need peak performance, this is the best collector you can get, right? It's also called the throughput collector. If we define throughput, that means time we spent in the application versus time we spent in garbage collection. That's what throughput means when we talk about that, right? And this is the throughput collector. So it's good for batch processing, scientific computing, data analysis, and other stuff. And to give you a better idea, it was a default collector from JDK 5 to 8. And this is how it works. In the young generation, we have parallel collection. That means we have multiple threads doing the garbage collection in the young generation, which makes it really fast, right? Because you stop the world, then you have lots of threads available to do the garbage collection, then you continue. So the stop the world pause in the young generation can be very small. In the old generation, same problem that we saw with the serial collector, just one thread. The problem with this collector is if you use that for huge heaps, then it might run very fast for some time until the to-nerd space, the old generation, runs out of memory. And then suddenly you have a long break for the garbage collection because just one thread. So if you know how your application behaves, then this could be a really good garbage collector, but you need some knowledge about memory usage, memory pressure from your application, and things like that. CMS, concurrent mark and speed. This is in principle, the heap layout looks nearly like I showed you the generational garbage collector. This is more or less how it looks. But this is deprecated because it had some problems. If I remember right, there have been so-called allocation stalls. That means if the application allocates more memory, that the garbage collector can't keep up with the allocation rate of the application. So that was one of the problems. So this is started from JDK 1.4 and still since JDK 13 it was available. It was deprecated in JDK 9 and removed in JDK 14. So if you're on 17, you can't even select it anymore. But by the way, who's on JDK 8? Someone here still? No, 11? 17? 21? Okay, cool. So like in 11, you could still select it. In 17, not anymore. So this is not a bad collector. It was the first one where they tried to keep the garbage collection pauses lower than 1 second, right? So that was the first time there was some kind of a predictable garbage collection pause. The max garbage collection pause time was 1 second, which makes it at least predictable, which is good. I won't go through the diagram. You will see it will get more and more complex. It's partly concurrent. So it could, for example, this could do concurrent marking and concurrent sweeping. Sweeping means freeing. And it was removed from JDK 14, as I mentioned, and deprecated already in JDK 9. So not that important. The next one, and that's a really interesting one, because this is, at the moment, this is the default garbage collector, and that came with a totally different principle. This is a so-called region-based collector. And to give you an idea how it looks like, remember we had these huge areas, Eden, survivor spaces, tenerd space. Here, we structure the heap and use regions. And the region size you can see on the left side. It depends on the heap size that you define. So let's say you define more than 64 gigabytes of heap, then you will get 32 megabytes region size. Each of these bigger squares is 32 megabytes then. And if you have less than 4 gigabyte of heap, each of these areas is 1 megabyte, right? So this is unassigned regions. If they are assigned, they will look like this. So that means you see the Eden region, we still have Eden regions, we have survivor regions, we have tenerd regions, we have humongous regions. And the name is really, if you have an object that is bigger than half the region size, you get the complete region. Well, sounds okay. But if your application is using a lot of big objects and you don't tailor the heap size correctly, it can lead to the fact that you run out of memory, even if you have lots of memory in your heap. Because if every object contains or gets a whole region, the rest of I can't show it here because it's up there, but maybe, yeah, you see this area here? This is empty, but it is reserved, right? Because that means if you're just a little bit more than half the region size with each object, you lose every half region of your heap because you only get one object in that. Okay, to make it more visual appealing, there's a little demo. We start allocating. I have 6 Eden regions. When they run out of space, we take the 2 with the most garbage first, and copy them into a survivor region. So it will happen in a second when this one is filled up. Now, check. There we go. It wasn't enough for one. We took 2 survivor regions here, and we continue allocating until the survivor regions run out of space. I have 3 defined in this example, and then we promote them into a tenerd region. I don't have humongous regions in this demo. But you see how it works, right? I can just allocate wherever I like. There's not really a rule. And again, this is an example, right? It doesn't look that random. It starts somewhere and it's filling up the heap slowly. And it's not like random like I did. It's just to give you an idea that even if it was once, let's say, an Eden region, it can be a survivor region, it can be a tenerd region, that this will change. This makes the whole thing way more flexible. And because it's small region size, garbage collection is fast, right? So that's another big advantage here. So that goes on forever, so I have to switch. With this one, the typical garbage collection pause is 200 milliseconds, right? Way faster than the other collectors, and it can go down to 100 milliseconds, which makes it a really good default collector. But keep one thing in mind, that the sweet spot of this collector is around 16 gigabytes of heap. And you can go up to 32, still okay. If you go bigger, it will work. If you go less than 16, it will also work. But the best performance you get at 16 gigabytes, right? So if you're smaller, you might want to try another collector if you run into problems performance-wise. And this is more or less a general purpose garbage collector for all kinds of usage. As you saw, most of the people just use it as default and it's fine. Which means the developers of this collector did a really good job. All right. Okay, clicker doesn't work anymore. So this is how it looks like. way more complex, as you can see. It's also partially concurrent. It's the default collector since JDK 9, and it can do concurrent marking. Next one of my favorites, epsilon. Who heard about epsilon? No one? It's the no collector collector. It's not a garbage collector, but it is. So you can use this garbage collector by using the switches on the lower right side, and you won't have any garbage collection in your application. Sounds awesome, right? That means you run out of memory like this, right? If you know exactly what you do, and if you know exactly how much memory your application needs, this is more or less the fastest option you have. It's at the same performance as the throughput collector when it doesn't do the to-nerd space collection. If you need last drop latency improvements or throughput improvements, that's the way to go, but really be careful because you might be surprised how fast you run out of memory without garbage collection. You can give it a try. You can start, it's done. It's like this. But if you know how to do it, it can be really fast. For example, if you do high-speed trading applications, these people use these kind of collectors for small services. Okay, Shenandoah. Who heard about Shenandoah? Nobody? One? Okay. So this is a garbage collector that came with JDK 11 or 9. It was developed by Red Hat. And this is the only non-generational collector at the moment, because with JDK 24, we will see a generational version of that. And then probably this one will go away. This is a different approach. It's also a region-based collector, but this is made for very large heaps, 100 gigabyte plus. And all the others that I show you now, same thing. So if you have, it's really fully concurrent, completely. There's not really a stop-the-world pause. There are pauses. They are just so small that we don't really take care about it. I think they guarantee around 15 milliseconds, if I'm right, which is very, very fast. Problem with these collectors that I show you now, the fully concurrent ones, keep in mind the performance is always lower than with a non-concurrent collector, right? The reason for that is, let's say you have 100 threads for your application. Now you do parallel collection. You stop the world. You have 100 threads for garbage collection. You continue, again, 100 threads for your application. Now you use this one. You have 80 threads, let's say, for the application from the 100, because the other 20 are used for garbage collection concurrently. So that means you will see a drop in performance when you use these kind of collectors, right? You just have to keep that in mind because they are praised like this is the new thing, but yeah, they come with some problems. This one is not available in Oracle JDK. That means really just the stuff you have to pay for, probably because it's from Red Hat, so they don't really support it. In OpenJDK, it is available, right? So every other distribution has this garbage collector. Yeah, the throughput is a little bit reduced because of concurrent GC. It uses load reference barrier, way too complex to explain here, and it will be generational in JDK 24. Next one, ZGC. Who heard about ZGC? That's the hot this year. So we have region-based collector. We only have young and old generation. There's no survivor spaces here. So if they are survived several amount of garbage collection cycles, objects will be just promoted in the old generation. Again, fully concurrent, made for very large heaps. To give you an idea, this garbage collector shines if it has 48 cores, 120 gigabytes of heap. Then it's really good. You can use it with smaller heaps, right, and less CPU. But because it's concurrent, it needs CPU, right? So this is something you have to keep in mind. If you would like to, if you really have high-speed application, huge applications, if you need last drop of performance, go with this one. For example, Netflix, they switched to ZGC. They saw a drop in performance of 3%, right? Sounds not a lot, but you have to pay for 3% cloud cost to get to the same performance that you saw before, right? And you need probably more CPU and memory to make it work, just to keep that in mind. This is also fully generational. In the meantime, the non-generational version that came with JDK 15 is already deprecated and will be removed in the near future. Yeah, already mentioned that. Last one in the list, because we are running out of time, C4. Probably nobody ever heard about that. And the reason for that, this is made by Azure. And ZGC is more or less a copy of this. And we did that already, I don't know, 12 years ago or longer. But it is in a paid product. It's our Zing JVM, and it has the same principles. So what I explain now also is the same in ZGC, right? So we have a so-called loaded value barrier, which is in ZGC, colored pointer, same thing, same algorithm. And as mentioned here, if you run on Linux, and we only support it on Linux, you need THP enabled, which it's better because then the memory page in Linux is bigger, and it means we can use bigger regions. To give you an idea how the marking phase works in that one and also in ZGC, I give you a short example. We have multiple garbage collection threads. We have the roots, which are the stack frames, the squares. Now the garbage collector goes through all the references and marks the object as live, and it triggers always the loaded value barrier. And now if an application thread does the same, right, and this is now the difference, the application threads allocates memory, and it will trigger the barrier, and the barrier will mark the cell directly as live. The garbage collector doesn't have to do the remarking phase, right, which makes it faster. Same for ZGC. It's just different names, but it's the same thing. Okay, and then it hands over to the garbage collector and tells you, look, here's another live cell. Okay, that's good. Quick release, another example. I'm not sure if ZGC has that, but if we have all these regions and we now do a compaction, that means we copy the stuff to new areas. So we start copying, right? And when we do that, instead of installing the reference, the forwarding pointer to the new location in the old object, what we do is we store the forwarding information in an off-heap page. ZGC does the same. It's always the same location. So we copy all the information there, and every time you see we have physical memory, the purple ones, and the virtual memory that we work with. Every time I have copied all this stuff to a new location, I can directly free the physical memory because the forwarding information is not in the old object header. It's off heap. And that makes it faster for allocation because the physical memory is already ready again. And now if an application threads try to access the old position, it will trigger the LVB, the barrier. The barrier is still there, right? So it's there and says, oh, there's no object anymore. And then the thread will look up in the off-heap page, take the new position, and update it. That means the next access will directly get the right position. That's the idea. Okay, I will just skip that. Same. This is the big question. Which collector to use, right? So we have throughput, latency, and resource usage. This is the three dimensions we can work with. To make it easy, you only can switch 2 out of 3. You can say, I would like to have very high throughput and very low latency. Sorry, resource usage won't be low, right? You can say, oh, I need very low resource usage, but very low latency. Sorry, you don't get high throughput. But still, with this, you can't really choose one, right? This makes it easier. If you don't care about pause times, then you're on the right side, right? That means runtime overhead is more important, then you probably use parallel or serial. If you say pause times is the most important part, you're more on the left side. If you have no idea, you're in the middle, and that's G1, right? Okay, overview, and this is more or less the last slide. This is an overview about all these collectors with all their properties and pros and cons, more or less. So I'm not sure if they collect the slides. If not, just feel free to ping me on LinkedIn and I'll provide it to you because I will change that every time I present it. Not this slide, but the rest. And I can send you the slides then because I didn't put it on somewhere officially because I changed it too often. And with this, thanks for attending. I was 3 minutes over time, so I hope you still have enough time for coffee. Thanks.